Hello everyone, we'll be doing a physics problem. This one's about lasers. So in this problem you're given the width of the box and it's asking for the de Broglie wavelength and the norm momentum at three different energy levels. So let's recall that the, de Broglie's wavelength is 2 times the width of the box over n. And in this case, lambda 1 is equal to 2 times 3 times 10 to the negative 10th meters over 1, and that should be 6 times 10 to the negative 10th meters. We can then apply this to momentum, and that is Planck's constant divided by de Broglie's wavelength. And we know Planck's constant to be 6.63 times 10 to the negative 4th joule seconds. And we divide that by 6 times 10 to the negative 10th meters. And as a result, you should end up with 1.105 times 10 to the negative 21st kilograms meters per second. Sweet. We could then do the same thing for part B, where n is equal to 2, and the 2's will cancel out, so you're just left with 3 times 10 to the negative 10th meters, and the momentum at n equals 2. The momentum at n equals 2 will be Planck's constant divided by lambda 2. And you should get 2.21 times 10 to the negative 21st kilograms meters per second. And part C, it's the same process again. I know it's tedious. I'll just do a shortcut. There we go. And P3, you guys know the process. Yep, it's 3.315 times 10 to the negative 24th kilograms times meters per second. So we got all our values, and it's asking us to compare wavelength to the width of the box. As lambda, based on the math, as lambda increases, the magnitude of the momentum also increases. So therefore, there's a directly proportionate relationship between the two. Okay, here's another physics problem related to lasers. I'll give you guys a few seconds to read this problem and figure out the solution. Okay, I think that's plenty of time. So in order to grasp this question, you have to comprehend the spectrum of an X-ray tube and its source. X-rays are generated from accelerated electrons colliding with the target. When high-energy electrons strike the target, many of them interact with atoms, lose energy, and produce heat. Only a small fraction of electrons interact with the nucleus and electrons of the atom, resulting in the production of continuous and characteristic spectra. The energy of the colliding electron is determined by the voltage it passes through before hitting the target. When such an electron releases its energy, it manifests as X-rays, either in a single instance or multiple instances. As a result, the minimum potential difference required to generate a specific wavelength of radiation depends on the efficiency of converting the electron's kinetic energy to electromagnetic energy of X-ray photons. For our sake, let's assume 100% efficiency. So we should have EV equal to Planck's constant speed of light times the wavelength of the X-ray, and if we solve for V, it is simply hc over E times lambda x. From here we can plug in our values, which is 6.63 6.63 times 10 to the negative 34th times the speed of light, and the charge of an electron is 1. Hold on. 1.602 times 10 to the negative 19th coulombs times our given wavelength of 0.1 nanometers. Okay, quick disclaimer everyone. You have to convert 0.1 nanometers to meters, and that is simply just 0.1 times 10 to the negative 9th meters. And after plugging everything in, you should get 1, 2, 4, 1, 6 volts, which is approximately 12.4 kilovolts. Okay, so this is another one. This one's on the difficult side. I'll give you guys a few seconds to read it out. And while you guys are reading, I'm going to draw a picture that'll hopefully help us. And hopefully you guys are done reading and thinking about a solution. So one way to approach this problem is to acknowledge that when electrons go from an L shell to a K shell, an X-ray is produced. So let's say this is K and this is L. Boom, boom. That creates an X-ray, and the energy of the X-ray is equal to the difference in energy between the energies of L and K. So mathematically it should look like this, which is an alternative representation can also be written in this manner, which hc over lambda equal to delta E. Now it makes sense for a change to be negative because it's going one shell up, so therefore energy should be negative. And we are given such values that E of K is equal to 8.979 kilo EVs, and E of L is given us 0.951 kilo EVs. And we know Planck's constant, and we also know the speed of light. Now, with what's given to us, let's see if we can use these values to find some answers. So hc over lambda is equal to delta E, which is E of K minus E of L. And if you guys do the math, that is approximately 8.028 kilo EVs. Now let's remember that number, and because we have the change in energy, we can solve for lambda, where lambda is equal to hc over 8.028 kilo EVs. And we know our constants. Let's plug them in, and we should have 1.542 times 10 to the negative 10th meters. Okay. And this answer can also be 1.542 times 10 to the negative 10th times a, and this is going to matter when we, this is going to matter for the next step. So we have lambda, now we gotta use Bragg's law. And what Bragg's law entails is 2d sine theta is equal to n lambda. And we're given theta, which is 74.1, and n is equal to 1, since it's the first order of reflection. So let's solve for d. Lambda equals 2 sine of theta. We have theta, and we have theta. We have theta and lambda. And as a result, we should have 0.802a. And that should be, let's see here. Yes, the answer is the spacing between the parallel planes. And there we go. Sweet. Okay, in case it wasn't clear, the reason why the answer is a multiple of a, it's because it's simply just a conversion factor. For any value times 10 to the negative 10th, keep the coefficient as is and replace the exponent with a. It's nothing above and beyond, it's just a way of simply expressing a solution. Okay, and here comes another one. This one's asking for the predicted value of this time for a laser pulse to travel from an observatory to a reflector on the moon. Okay. It wants to know time, separation, and angular divergence. So we're also given that the precision is, the separation can be measured to a precision of 15 centimeters. And it wants to know about the uncertainty and travel time. Okay. So part A wants to know the predicted value of this time for a laser to go from Earth to the moon. And if you guys refer to your appendix in your textbook, the distance between the moon and the Earth is 3.82 times 10 to 8 meters, at least approximately. And the speed of light, as we should all know, is 3 times 10 to 8 meters per second. This is approximately 2.55 seconds. Don't believe me? Work out the math. Okay. Now for part B, we will deduce the uncertainty in time measurement, and we're going to let it be identified by this equation, where, let's choose x. X is equal to the time times the precision, which is 0.15 meters, over 2 times the speed of light. And as a result, we should have 5 times 10 to the negative 10th seconds. So x is our uncertainty in time measurement, and that is equal to the time from part A, the time it takes for light to go from the moon to Mars, times this precision, divided by 2 times the speed of light. Just thought I should make it that clear. And as for angular divergence, we have theta is equal to 2 arctangent of 1.5 times 10 to the third divided by, let's just identify its variable as d. And if I was to use the small angle approximation, I should have the result of... Oh wait, hold on. Oh, misread my calculator. Okay, so the angular divergence is 2 times arctangent of 1.5 times 10 to the third divided by distance from the two planets, which is 3.82 times 10 to the 8th meters. This will yield a result of 4.5 times 10 to the -4th degrees. I'm not sure if the answer is supposed to be in radians, but you guys can convert that at your own time. Oh yeah, I forgot to disclose the 1.5 times 10 to the third, this value right here, in part C, you're given the diameter of the moon, which is 3 kilometers. The 1.5 times 10 to the third was actually the radius of the moon. And the units cancel out on your left with radians, and I hope that clears things up.